Thank you. Awesome. Okay, well, welcome everyone. Today, as you know, we have a colloquium, but as always, you have to hear 10 seconds from me to remind you about everything that we are planning for next few days. So the first thing to mention is this Friday. So again, now we have main events happening on Fridays as well. So please don't forget that. And we are starting to move some of the work in progress to Fridays. And that's what's happening this Friday. So April 17th, we will hear from Jimena and Feng. So the imaging galaxy distortions with uncertainty. So basically this is Emma's and Chitska's project. So we'll hear more about what they're doing. And on Wednesday, you will hear from the project that Sandeep and I are leading. You will not hear from me except to hear these intro slides again. So you will hear from Anirban, from Aiden and Jarvis, who are working on our project. So hope you'll be there to help us with the places, like all the things that we're stuck with. So hopefully both of these are going to be cool discussions. Another thing that I keep reminding you every time is SkAI Sprint and SkAI Fest, May 28th and 29th. Please be available for that. Mark your calendars. SkAI Sprint is about bringing software engineers that work with us to do a lot of like co-working and just sprints to do all kinds of cool things. And then SkAI Fest is just an internal event here for SkAI to share and present about all the work that's happening, whether those are like SkAI funded projects or something that's related but still happening and here at SkAI. And another thing is SCOPE, Science Communication Online Program for graduate students and postdocs. That's starting the program starts April 20th. So it's a long program, but remember, if you have not registered for this, the deadline should be this Friday. I believe it says April 20th. But I think it's this Friday. If you have any other questions, please ping Chitska. She knows all about this and is organizing this. So again, yeah, do not forget to register. And with that, I will call Chiwei. So we go to the main event.
Hello. So thanks everybody for coming. Today we're super happy to have Keith Bechtol here to give us, sorry, is that something I need to serve? It's okay? Okay. To give the colloquium. So Keith and I went to grad school together. We basically I just followed him around. This is just general story. I was doing LSSD, he was doing Fermi stuff. And then he went to KSCP to do DES, and then I moved to somewhere else to do DES. And then after that, he went to, I think he went to Wisconsin for a short postdoc. And after that, he actually worked in the Rubin kind of project for a few years before he started faculty at Wisconsin. So I follow him around in the sense that I started doing DES after he started doing DES. I went to Chicago after he went to Chicago, and I came back to LSST after he started building the LSST. So that's a good indication that Keith has good taste. And yeah, and you'll hear all about it today. So Keith is currently associate professor at University of Wisconsin-Madison. He is also the associate chair of graduate program. So for all the graduate students, if you have any questions about the graduate program, you can ask Keith. He is also, I always get this wrong, so I need to write it down, system verification and validation scientist for Rubin, and is the desk deputy spokesperson. So with all that, he's going to talk about Rubin today. And that's welcome, Keith.
Audio okay? Good, good. How well do people know Rubin Observatory here? Just out of curiosity.
I mean, how
Enthusiastic Rubin users or curious?
Curious.
Curious? Okay, okay. So I've worked on Rubin Observatory for about 10 years now. And basically over the last year, like all I think about every day from when I wake up to go to sleep is starting the LSST survey. It's been this really exciting, intense period. And I'd like to try to share some of that story with you. So the objective of Rubin Observatory is to deliver atmosphere limited image quality across a 3.5-degree field of view on an 8-meter class telescope. And it turns out that if you can deliver this, it is just a tremendous science opportunity in so many different areas of astrophysics and cosmology, and in data science as well, because of the sheer volume of data and the complexity of that data that will be generated. So the idea is that we'll take a digital image of the sky every 35 seconds, every night for 10 years. In total, that's 2 million individual images with a 3.2 gigapixel camera. We create a multicolor time-lapse movie of the full night sky visible from Chile at arc-second resolution. So that's the goal. And then in addition to that, we serve science-ready data products that have been validated and have all the software associated with that to a global community of thousands of users. So to give a sense, like on the Rubin Observatory Slack workspace, I think it's like 4,000 or 5,000 people right now, and the database is being scaled for 10,000 users. So no pressure. Rubin Observatory, if there's like one thing to describe it, it's big, right? And it's really hard to convey just the sheer scale of everything about the project. I've spent several months at Cerro Patron at the summit over the past year. This is a picture. You can see Alana Urbach standing next to the telescope, and it's just massive. The building is huge. All the infrastructure surrounding it. It's just a really incredible facility. So what makes LSST special? This is the Legacy Survey of Space and Time that will be conducted by Rubin Observatory over 10 years. First is that it's extraordinarily wide in terms of its coverage on the sky. This is showing basically the coverage of one single exposure with the LSST camera on Rubin Observatory. You can see it as compared to, for example, the Hubble or the JWST field of view. When you have this really large field of view, you can map the sky very quickly. And so this is basically an inset showing a region of sky that we imaged during the early on-sky commissioning period. And you can see that the field of view is 7 full moons across, just to give a sense of scale. So this is a region like if you were to hold up your fist, right? It's sort of roughly that scale on the sky. The entire facility has been designed to map the night sky as quickly as possible. And so what this movie is showing is a night just a couple weeks ago on the 5th of April, we took about 850 individual science visits in a single night. So you can imagine like every 35 seconds, you're basically slewing to a new position on the sky. And you can basically see that over a period of several hours, we're basically able to cover large swaths of the sky visible from Chile. And so the idea is that we'll basically map the entire visible region every couple nights. And so that's what we mean by this time-lapse movie over 10 years. Basically, every spot on the sky will be imaged something like 800 times over a period of 10 years. The images are also incredibly deep and rich with knowledge. So this was the state of the art for many years, the Sloan Digital Sky Survey. This was kind of the beginning of survey astronomy in terms of getting so many astronomers into this field and into doing these large-scale statistical data analyses with astronomical data. So this is a region of sky as viewed with SDSS, and this is the same region of sky as viewed with Rubin. So if you go back and forth, right, you get a sense as to just how much information content is in these images. So let's talk about the story of on-sky commissioning and early operations. So when we talk about commissioning, sometimes people ask me like, oh, did it just start when you go on sky for the first time? And the answer is it actually takes place over like a decade, right? So as all of the individual components of Rubin Observatory were being delivered, they were all tested individually, and then they were shipped to Chile, and then we would do additional testing at the site. We would basically integrate all of the individual components, and every time you put two pieces together, you basically validate that it works, not only individually, but also together. And so you basically repeat this process over and over again, creating higher and higher fidelity tests. So basically, I was the lead scientist in the systems engineering group. I'm not trained as a system engineer. I'm trained as a PhD physicist, but it was an extraordinary opportunity to be able to work with these professionals in all different areas. And so I learned much more about systems engineering than I ever thought that I would. This is an example of one of the activities that we were doing prior to the full integration of the telescope. So within the Rubin Observatory facility, there's this giant staging area. And you can basically see this is just like a typical view on any given day for a period of several years. Basically, the components would be delivered to Chile, and then you'd have everyone, doing all of their tests, moving the actuators, testing the command and control, measuring all the telemetry, basically checking that everything works before it actually goes up onto the telescope itself. Then what we would do is that once we started integrating the components, we would actually take them for a test drive. And so this is an example where you'll notice that we don't actually have the mirror. We have a mass simulator. So basically this big cross of metal was designed to have the same basically envelope and same mass distribution roughly as the mirror. And so what we would do is we would actually practice driving the telescope, measuring all of the inertial forces that would be experienced by all of the components. And you can kind of get a sense how this allowed the team to practice going through many of the operational procedures that we would need to do on SkAI. We also did full operations rehearsals where we would simulate, for example, several nights of data, and we would actually run it through the data acquisition at the summit. So we would go full end-to-end analyses of actually like designing the observations, creating the simulated set of observations, rendering the pixel images, pushing those through all of the data processing chain at the summit and all of our data facilities, running those through our calibration, through our co-edition, all the way through generating object catalogs and even difference image analysis. So we basically exercised all of the different components of the data processing chain. And we actually did this multiple times to get ready for the start of on-SkAI commissioning. So our first opportunity to do a full end-to-end engineering test was with a commissioning camera that we call ComCam. So the way to think about ComCam is that if the full LSST-CAM field of view is composed of these 189 individual detectors in a mosaic with these 21 basically arranged into 21 3x3 groups that we call rafts. So ComCam is effectively the central raft. It's designed to have all of the same interfaces as the full camera, just on a smaller scale. And so before going on SkAI, we installed ComCam and we took a selfie with the team so you can see people inside the dome. Then it was time to go on SkAI. And due to all of this preparation, all this work that the team had done over many years, all of the measurements, all of the metrology, all the testing, it basically worked on the first night, which everyone was really excited about. So the ComCam focal plane on the very first images was within about 1 millimeter of being in focus. And we already had basically lookup tables to correct for gravitational distortions as we would start moving across the sky to refine the focus and alignment. Within just a matter of minutes, we were delivering total image quality at the level of around 1.5 arc seconds. So our goal was to get to the sub-arc second level, and we were already doing that on the first night. And that's even without all of the optical adjustments and environmental controls in place. And the data management system, because we had done all of these operational rehearsals, because we had gone through all these exercises, basically we were able to take those in-focus images, run them through the single frame measurement, and produce initial astrometric and photometric solutions for the individual visits within minutes of requiring the exposures. So we basically knew in real time that the system was working. This is an example of one of the images from that very first night with ComCam. So again, it's shown within this wireframe to represent what the full LSST-CAM field of view would look like. And then this inset here is showing basically the part of the sky that was imaged with ComCam. So the team was super excited about this. I recently read a biography of Margaret Hamilton. Do people know Margaret Hamilton? So she coined the word software engineering. She was the lead software engineer for the Apollo program before software engineering was even like a field. Like she was basically working with the group that created this, all the navigation systems for Apollo. And in this biography, it basically says that all this attention was on Apollo 11, the first moon landing, but for the Apollo team, the Apollo 8 mission, where they rounded the far side of the moon for the first time, and then they took the famous Earthrise photo, and then came back to Earth, that moment for the team in terms of knowing that it was possible to accomplish the mission was like a really big milestone in terms of building confidence. And I would say that the ComCam on SkAI campaign, it was 7 weeks. It was extraordinarily intense. For all the successes, there were many challenges too. We learned a lot, but I would say it was really kind of this like critical moment in terms of giving us confidence that we could go to the full integrated observatory. So the next step was to integrate the full LSST camera. It's massive. You can get a sense here looking at all of the utilities, right? So it's basically cryogenic cooling. It's a vacuum. It's got to have ways of dissipating all of the heat. So it's about 3,000 kilograms to give a sense, like the size of a car. You can see the engineers for comparison. And this is the moment where this is basically the interface between the telescope and the camera. So when the camera gets installed here, we have this integrating structure, and then that will actually get mounted onto the top end assembly of the telescope. So that happened about a year ago. In fact, actually today, April 15th, is the 1-year anniversary of the first night sky images with LSST cam. It's worth mentioning that it's a 3-mirror system. And so when you see an image like this, you're actually seeing reflections off of the secondary mirror into the primary tertiary surface. So this is actually the focal plane of the camera seen in reflection. When you're standing there on the platform, like when you're standing up there and you're like in between the 2 mirrors, it's really, it's really like mind-bending when you're there. Okay, so this was when we were taking the first image. Most people look really happy. You can see I look really nervous because this is this is the moment that it's like go time for on SkAI commissioning. This is like what we had been preparing all these years for. And the very first image, right? So this is the first image, night of first photon, 1 year ago today. This is one of those 189 detector images, and it was within 3 millimeters of optical focus. So what you're seeing here, these kind of donut-looking images, these are basically slightly out of focus images of the telescope pupil. And so when you're out of when you're pistoned a little bit out of focus, you see the pupil, basically the primary mirror in this shape. Okay. So within about 13 minutes, we were able to run a manual focus sweep. And we got to a PSF of about 1.8 arc seconds across the field of view. So we knew that we were close, right? That it was working. This particular visualization, we'll see some more examples of this throughout the talk. What it's showing is that on each of the individual 21 science rafts, it's basically showing a zoom-in postage stamp around a bright star, so you get a measurement of the PSF. And so, we were really excited about this from the standpoint of the first minutes, but you can see these PSFs have a lot of structure. Like you would not want to do science with this image, right? There's all kinds of structure that would be very difficult to model. It's much larger than we would want it to be. But the point is that we were close enough to capture that we could get right into our planned on SkAI engineering tests. So within 3 nights, so this was on the 18th of April, we were able to run the active optics closed loop system, and I'll describe that more later in this talk. But basically, you refine the optical solution through iterative adjustments of the optics, measurements of the wavefront. And once we were able to run this AOS closed loop, we were able to get a PSF full with half max of 0.7 arc seconds across the full field of view. Right. So we knew within even the first 3 nights, that the system like fundamentally had the capability to deliver the science that we wanted to do with LSST. You can see here, PSFs, much smaller. There's still a little bit of structure, a little bit of ellipticity. And that's a lot of the work that we've been doing over the past year, is just making this performance more and more reliable. So at this point, everyone was happy, right? This was good. So one of the first things that we did is that we wanted to share the scientific capabilities of this new facility with the world. And so one of my jobs was to basically work with the team that was designing the observations that we would look for a first look big media event. So the goal was, basically make newspapers, headlines around the world, like front page in the New York Times kind of thing. And so what we did is that we basically developed a strategy of having selected targets that would emphasize the enormous field of view and just the sheer information content that was available in these images. And so one of the fields that we selected was this cross section through the galactic plane around the Trifid and Lagoon Nebula. And you can see, basically this entire field is filled with stars. And you can just zoom into this image and you just see more and more stars as you just keep on going in. When we were taking this data, it was like, there were like moments where people in the control room were just speechless, because you could just see in the raw images the amount of information content that was available. It was really staggering. Like, if you're just not used to looking at a 3.2 gigapixel image and just scanning around and just seeing all the detail, it was like nothing we had ever seen before. We also took a selection of extragalactic fields, and so basically, one of my jobs here was basically to design the observations and to orchestrate the observing campaign to take all of this data. So I was like in Chile, basically working with the AOS experts, getting the optics tuned up, and we were taking this data within about 2 weeks of going on SkAI for the first time. And so it was really challenging, right? There were a lot of things that weren't working quite the way we expected. There were a lot of obstacles that we basically had to navigate. Each night was different, but we got some amazing images, right? So these are just sort of representative. And one of the things that we did, one of the ideas that we wanted to highlight was that LSST is designed to be this data set that is open for exploration for all different areas of astrophysics, right? Milky Way science, the solar system, cosmology, the extragalactic transient sky, right? So we really wanted to be able to tell that story, that there's all this different science that you can do within a single image. And so what we did is that we basically took over a period of about, it was probably like maybe 5 nights, we took about 1,000 images of this field. And the idea here is we would basically be able to create a movie of everything that was changing. And so when you build the COAD, you can filter out the things that change. But if you actually leave in all of the objects that are, that are only present in one visit, what you see, I'll blink back and forth here. Oops. Can you see these linear features coming in different colors? So these are actually asteroids in our solar system. And they have this multicolor appearance because we were switching between different color filters, right? So we would basically, take image through, you can think about it as like blue light or green light or red light, right? And so we take sequences of images just on the same field. And so over a period of a couple hours, the asteroid would move, right? And so every couple minutes, you would basically see a new dot when you took an image of this field. And so you'd basically get this time series, like a mapping between time and then position on the sky. And so we worked with our communications group to basically think about how to visualize this data and make it appealing to the general public. And so this is one of the visualizations that we came up with, is showing this time series. So each frame is basically an individual exposure, but because we have this enormous field of view, we could actually measure about 2,000 newly discovered asteroids in this one set of data collected over a period of about 5 nights. And so you can see each one of these dots here is representing newly discovered asteroids from Rubin Observatory. So over the full 10 years, Rubin will discover probably like several million asteroids. And so this is just the first set.
Quick question.
Yeah.
You explained the color of the asteroids, but what about the color of the galaxies? What does that correspond to?
So that same image that we were, so basically it's the same field is where you have the asteroids in it. And so the colors of the different galaxies, these basically correspond to different types of galaxies. So depending on their individual star formation history, depending on, for example, the metallicity of the stars, how much dust is present in the galaxy, you get different colors. And then that intrinsic color of the galaxy will then be redshifted. So if you're basically looking at galaxies at different points in the history of the universe, that light emitted from the galaxies will appear at Earth with an adjusted wavelength, basically modified by the expansion of the universe. And so we actually get information not only about the type of galaxies, but also about their age and distance as well.
Okay, so you are doing the red, green, and blue filtering, and then just making an RGB-like image.
Correct.
Okay.
Correct.
So it's not like a after the fact post-processing analysis.
That's right. I mean, so we can map to color channels, to make it appealing to humans, because we actually extend into the near infrared, into the near ultraviolet. So we actually extend beyond the visual band. So not all of these colors you would actually be able to see with the human eye, but we can represent it in a naturalistic way. We spent hours and hours and like countless telecons talking about the color scheme. It was a lot of discussion. We actually developed a new color scheme to represent these data.
Thank you.
Yeah. Here we go. Good. Okay, so after taking these targeted, like deep drilling observations of specific fields to create this kind of cinematic, experience with the solar system objects and all the variable stars and everything that was changing in those fields, our next goal was to show not only that we could close the loop and get good optical convergence, basically sharp images at a single point on the sky, but that we could also survey broad swaths of the sky, that we could basically take large regions and move quickly within the night to cover those large areas of sky. And so this was our so-called science validation surveys. We had 2 different components, a wide area survey, so you can basically see this stripe here. And we chose this because it crossed the galactic plane. It had a large extragalactic region, and this stripe here is oriented along the ecliptic plane. So basically where the objects in our solar system orbit as viewed from the Earth. And so our goal was to try to enable as many different science cases as possible with this single data set. And so over a period of months, we took more than 10,000 visits in this wide survey. It ended up being quite challenging because we had lots of weather. We had piles of snow. We had ice forming on the dome. We were doing this in the Chilean winter at an elevation of 2,200 meters, 2,600 meters. So it's 8,000 feet, and you're exposed to all kinds of weather conditions there. And so this is kind of what happened, is that we started in the survey. We were initially making excellent progress in our cumulative visit count relative to the simulation, what we had expected. And then we got really slammed by the weather. You can see that our rate of acquiring new images really fell off. And in addition to that, we started realizing that the image quality needed more work, that we basically needed to devote more dedicated on-sky engineering tests to improve the consistency of the images. But during that same period, we were able to take observations serendipitously of an interstellar object that was passing through the solar system. So just because we are covering this wide area of sky, we just happened to take images of this interstellar object even before it was discovered with other telescopes. So just kind of gives a sense of the science that becomes possible when you have this really really powerful surveying capability. And then we got to the end of the science validation surveys. And at that point, we basically knew that the system was functionally capable, that we could drive it in a mode that we could take several hundred visits per night. We could, we could routinely get to sub-arc-second image quality, but we couldn't do it consistently throughout the full night, every night. And so what we're doing right now is we're calling it an early operations phase, but the goal is to show that we can have this sustained, reliable, repeatable performance that would allow us to have confidence starting the 10-year survey. This is our main emphasis. So we basically had this transition from the construction where we basically declared all of the major components of the observatory to be functionally complete. And now we're kind of in this tuning up stage. So one of the next milestones was Rubin first alerts. So this is when we actually started sending these real-time notifications of these differences in the sky to the science community. And so on the 24th of February, so just within two months ago, we had built up enough images over regions of the sky. We had robust templates so that we could compare the new images to the prior template images, and we could start doing the difference imaging at scale with a high enough fidelity that we felt comfortable that we could send out these alerts. And so for a couple of days, we basically just took these intensive observations of fields where we had the template images deployed, and we sent out about 800,000 public alerts on the very first night that we started sending these to alert brokers. And this was really fun because in real time, we had been working with these community alert brokers, doing all of this testing as we were commissioning. And so on the night of the first alerts, they were basically able to add points onto the light curve of objects in real time. And so literally within minutes of taking the exposures, we could see them adding points to the light curve. And these are just two example supernovae that were being characterized during that period. So as of now, in April, we are now consistently distributing these alerts within 2 minutes of the shutter close. Basically, all of the data management systems have been tuned up to allow that to be possible. These are just a selection of some of the difference objects that were uncovered on that first night. So you can see supernovae, active galactic nuclei, solar system objects, variable stars, all of these being identified in real time so they could be included in the press release the following morning. So this is a summary overview of how we actually used all of the on-sky time during this on-sky commissioning period. And when I look at this, it tells a story, and that might not be immediately obvious if you have been sort of immersed in this over the whole past year. But a way to think about this is that the gray and the black correspond to the evening and morning twilight. So basically the times when it's dark enough that you can observe the night sky. Our goal is to observe continuously between the minus 12-degree twilight, so the gray points, every single night. That's our goal. During this on-sky commissioning period, you'll see that we often were not starting at that goal. And that's because it was basically an active construction site. So we were doing active engineering work during the day. So we would have something like 80 people at the summit doing engineering work, tuning things up, adding new components. And then they'd put all that stuff away, and then we'd go on sky. And we basically repeat this every 24-hour cycle, right? So we were this active construction site. And then we also were closing early as we were establishing confidence that we could, close the dome. That basically there could never be a situation where the sun would rise and the telescope optics would be exposed, because that would be observatory ending event. So the way to read the colors, basically each one of these points corresponds to one visit on sky. The orange is when we were doing dedicated on-sky engineering observations. So you can see that at the very beginning, we're mainly doing these dedicated on-sky engineering. Then the blue is when we were using our feature-based scheduler, basically our logical tactician that drives the observations for science imaging. This blue period here is when we were doing the Rubin first alerts. This is when we were building lookup tables. This is a period when we did sustained observations in a mode like the full LSST survey to show that we could survey the sky. And then we had these periods of bad weather. Basically, these blocks here are when we had winter storms and we couldn't observe. And you can see that we basically transitioned back to engineering because we realized we had more work to do on the optics. One thing you'll notice is that there's lots of gaps, right? There's lots of, these all correspond to faults where we had to recover, we had to realign the optics. Where you see the green here is where we were doing the survey, but we had to stop to realign the optics partway through. So you can see there's lots of interruptions, even though we have some contiguous hours of stable performance. If you compare that to, this is the early operations period. So this is now showing 6 months starting in late October up through the current time. So we basically had a month where we were doing dedicated engineering work between the commissioning period and the early operations. When we came back to early operations, we were really focused on collecting a lot of engineering data to try to diagnose these challenges with the optics. But then starting kind of in January through March, we did a trial run to see if we could improve the performance in survey mode observations. We decided it still wasn't good enough. And so you can see we're back in this really intense mode of engineering right now. But one thing you'll notice is that look at the blocks of time here, right? There's just contiguous observations, almost full nights. And you'll notice that we're starting much earlier. We basically got to a point where we were much more comfortable with our routine of transitioning from daytime engineering to nighttime observations. And we also got to the point where we could use the end of the night as well. We had enough confidence in the dome. And so you can see now we're basically utilizing the full night most nights. So our on-sky efficiency is much higher now. So let's talk about the as-built system performance. So one of the things that we did is we basically, while we were commissioning the telescope, the camera, we were also using our data management system to gather all this data, to process it in real time. So we had 4 different data processing campaigns that were going continuously throughout this period to give us diagnostic information about all of the images. So basically all the plots I'm going to show are the result of all the hard work that was done on the data management side to actually process this data quickly enough that we would get real-time feedback and actually use that to adjust our plans during the night and then also like on daily and weekly timescales. In terms of the astrometric and photometric performance, basically our ability to locate objects on the sky and to measure their brightness, these are meeting spec. They are really outstanding performance. The astrometric repeatability is at the 10 milliarcsecond level and is limited by the atmosphere turbulence. And then our photometric repeatability is at the 4 to 5 millimag level. So that's about like 4 to 5 parts per thousand, roughly. So sub percent accuracy on the repeatability of the measurements. This is just some visualization of when the astrometry is limited by the atmosphere turbulence. You can basically see in the residuals the structure of the atmosphere, basically. So these wavy patterns that you see is basically turbulence in the atmosphere that's modulating the locations of the stars as they're measured on the focal plane. So we're basically getting like a measurement of the atmosphere turbulence in some sense. And you can use Gaussian processes to model this out on a visit by visit basis. Also, we have really high quality calibration data. So you can see in this flip on the right panel, basically our ability to calibrate all of the individual exposures on the focal plane relative to each other. In terms of our overall performance at the summit, we are having, we're able to show a demonstrated increase in the overall efficiency. We have fewer faults, fewer interruptions. Our visit gaps between individual exposures is now down to a median of 8 seconds while we're surveying the sky. So basically take an exposure, slew to the next position, take your next exposure 8 seconds later. We're utilizing nearly the full period between the -12 degree twilights. And if you actually look at, what is the ratio of how many visits we acquire on a typical night when we're in survey mode observations relative to the absolute ideal that you could get, we're typically at the level of about 0.75 to 0.9. So not yet at 100, not yet at 100%, but getting close to that benchmark. In terms of the delivered image quality, we're now getting a median delivered image quality of about 0.9 to 1.1 arc seconds in terms of the PSF with half max. And we estimate that the instrument contribution to this, so the sort of, if you could back out contributions from the atmosphere, for example, we think that instrumental contribution is at the level around 0.45 to 0.5 arc seconds. We do see that many of our visits have a larger ellipticity than the design requirement, and this is where we've been focusing a lot of our attention. And there's also gradients in the PSF size and shape across the field of view, and that's where a lot of our engineering work is going into now, is to basically make that better. Oops, there you go. But one of the things that you can do is you can compare where we were during the science validation survey, so basically kind of July, August, September, to where we are today. And so this was during the SB surveys, the distribution of the PSF full with half max and the ellipticity. And I'm going to show you, this is where we were when we did our extended pre-LSST observations, kind of in the January, February timeframe. And if you blink back and forth, you can see that the tail of the distribution, basically these large PSF full with half max, right? If you go back and forth, you see that we're much more consistent now, right? And the median delivered image quality in several of the bands, kind of like the peak of this distribution, is now at the arc second level. We still have a bit of a tail, right? And so this is what we're working on now. We know that we can do better than this, and we think it's worth the investment, considering that it's a 10-year survey. This is just another way of looking at the cumulative distributions. Same information, just represented in a cumulative distribution rather than a PDF. And this is another way of kind of telling the same story. The histograms here are showing our estimated instrument contribution to the image quality coming from the optics and basically the limit of photoelectrons diffusing in the detectors themselves. And so this is where we were during the science validation surveys, right? With this much broader distribution. And this is where we are now, right? You can see this is much tighter. So this is an indication that we are making progress through a lot of this engineering work that we're doing right now. This is an example of the typical first thing that I look up when I wake up each morning. This is the first thing I look at. Basically, it's all the telemetry that we gather through the night. So we have all the information about the delivered image quality, where the telescope was pointing, our thermal control of the system, all of the degrees of freedom of the active optic system. So basically, each one of these corresponds to different types of optical aberrations and how we're adjusting our degrees of freedom to tune up the telescope. Basically, it's this very challenging control problem where you have noisy measurements and you have a delayed response because it takes time to compute the wavefront and then compute the correction and then apply that to the optics. So you're typically having a lag of at least two to three visits. So it's this challenging control problem, and we use all of this information to try to improve the optical performance and make it more and more consistent, good quality imaging. I think a picture, this is where like a movie is like really helpful. So this is taking that same information from that night and basically showing this view of how the PSF evolves across all of the visits. So again, this is something like, of order like 600, 700 visits. And as you're going through this, like you see sometimes the PSF is nice and round and small, but there are sometimes these excursions where you see these anomalous shapes, right? So basically throughout the night, as we're constantly slewing, moving across the sky, you have different temperatures, different gravitational vectors that are affecting the optics. The thermal environment within the dome is changing constantly. And so we're basically trying to correlate all of this telemetry, using that to inform our feedback loops, and to basically make the performance more consistent. But this is basically what we're working on, is how do we get this more stable? One of the tests that we've been doing is if you just pick one spot of the sky in telescope coordinates, so like fixed elevation, azimuth, don't change the rotator angle, don't change the filter, just stare at the same location on the sky, like the simplest test that you can do for the closed loop, and run in that mode for several hours. And so we've done this test, over the past couple weeks on multiple nights, and you can basically plot how does the optical performance vary across the focal plane from night to night. So each one of these grids here of 4 plots is showing one night of data, basically taking an average across hundreds of individual visits. And I'll just call your attention to the upper left-hand plot. So the color bar here is showing the median PSF full with half max, so basically the sharpness, the width of the PSF. And what you can see is that across multiple nights, like if you can compare this upper left panel in the different nights, you have the same basic structure. So somehow the telescope is converging to a suboptimal optical state, okay? And it's doing this consistently, so there's variations within the night, but also somehow the target that it's using for convergence is off, right? And so this is part of what we've been trying to diagnose. How can we make the image quality more consistently uniform across the field of view? So I'll describe some of the performance optimization efforts that are ongoing right now. There's a long list, so this is why we're still doing the engineering work. We think that a lot of this work we may be able to continue in parallel with starting regular survey observations. And so we're basically trying to front load all the tests that we think have the most diagnostic capability and where we wouldn't be able to do them as easily while running in a survey mode. Some of the new features that we've deployed is that we now have the louvers. So we have better air circulation by basically opening up these large panels on the dome to let air flow through during the night. So this is what those louvers look like. You can see that we actually have many more that we would like to open, but the components are still being delivered, and they weren't available until the past couple months. And so we've basically been trying to do all this commissioning work, but with a dome that's like not yet fully complete in terms of all the capabilities that we would eventually want it to have. But even with this subset of louvers installed, we can see that the sharpness of the images, basically the contribution from the dome seeing, has been reduced. And as we add more and more louvers, basically we get better and better image quality. So this is one of the areas where we're working. We've also noticed that when there's temperature gradients across the glass of the mirrors, that they actually change the optical figure in a way that's measurable. So it's not mirror seeing. It's not like the heat coming off the mirrors. It's literally the shape of the glass is changing in predictable ways that correspond to specific optical aberrations. And so one of the things we've been working on is basically improving our control loops, our predictive models for how the temperature will vary. And we're also, there's thousands of nozzles that basically circulate air through the mirror to control the temperature throughout the night. And so we're basically optimizing how much air is flowing through those nozzles. And what you can see is that the lines here are showing basically the fraction of the time that we're in compliance. And so this is when we were adjusting the nozzles. Now we have the new nozzles installed. Right, we're getting more and more consistent with basically being able to maintain the mirror temperatures within our target range. We are adding, ways of controlling heat sources. So this is a neoprene cover that was installed to cover a hot region near the optical path around the camera. Basically, there's these struts that move the camera for fine positioning. We've now covered that to insulate the heat. But But the big thing that we've been working on is the active optics system, basically this whole mode of controlling and refining the optics. And so effectively, what we're trying to do here is, these mirrors, the primary mirror is about 8 meters across. It's about 75 grams of silver, right? And we're basically trying to control its position at about the 100 nanometer accuracy relative to all of the optical components. And we can't do this without active control. This is challenging because this is a massive instrument, right? So the whole telescope mass is about 350,000 kilograms. The top end assembly is about 30,000 kilograms. So the whole thing flexes. It actually moves by like a couple millimeters, right, as we move through elevation. And it changes throughout the night. So if we were not making corrections, we would actually drift out of focus within a matter of minutes if we weren't actively making corrections. So we have many different degrees of freedom that we can control. We have hexapods for the fine three-dimensional positioning of the mirrors and the camera. And all of this needs to be controlled. So we slew really fast on the sky. So we basically slew to a new position, have to get everything configured, but then 30 seconds later, we're slewing to a new position. So we're constantly going through this enormous dynamic range of slewing and then tracking at a new position. And we do this, hundreds of times each night. So the way that we do this is with the active optics control system. And given that we don't have too much time, I'll just show some pictures to kind of give a feel for how it works. So the idea is that we have special sensors located on the corner of the field of view. There's 4 of them, and they're split. So they're intentionally located slightly intra and extrafocal of the rest of the science focal plane array. And what you see is that because they're 1.5 millimeters out of focus, you see these donut images of the pupil. And when you have this information, you can actually constrain which of the specific degrees of freedom you need to adjust to improve the optics. You get much more information from these out-of-focus pupil images than you get from the PSF itself. It basically tells you how to correct. And so on the right here, you can see an example of what do these pupil images look like compared to the in-focus, right? So we're basically trying to use the out-of-focus donut images to refine the optics. So we do this through the wavefront estimation. Basically, we measure by looking at the donut shape, we can basically infer what these variations across the optical wavefront are. And to give some intuition for what that looks like, these are a set of the different types of optical aberrations that we're trying to constrain. These are basically exciting one of those modes individually in a simulation. When we do this on SkAI, basically all of these modes can be present, right? So we're basically trying to disentangle all of this information and then search through this parameter space of 50 degrees of freedom to figure out what we need to adjust to sharpen up the images. You can see that a lot of times there's actually structure across the field of view. So for example, if you're tilted, right, you can be out of focus on either side, but in focus in the middle, right? And so there's all this kinds of structure that can be present that actually varies across the field of view. So we have all of the degrees of freedom, and it's actually way too many to control if you think about the individual actuators that are applying forces to the mirrors. So what we actually do is we think about it in terms of the degrees of freedom that are more intuitive in terms of an orthogonal or a nearly orthogonal basis set. So basically thinking about how the mirrors can flex. And so this is showing the 20 bending mode degrees of freedom on each of the mirrors. We have to measure how the optical response of the telescope changes when we perturb each of these. And then even this turns out to be too much degeneracy. So what we actually do is that we basically identify, we define a new orthogonal basis that actually has the goal of isolating specific ways of perturbing the optics that are more correlated with correcting specific aberrations. So this is an example of what that looks like. And basically all of these steps are involved in terms of refining the optics. I think we're getting a little bit tight on time. And I think those are some of the key elements that I want to talk about with the AOS. Effectively, all of this needs to be combined in an iterative way. So you're basically constantly acquiring new images, you're estimating the wavefront, you're deriving the corrections. And so the goal is that you start off with a PSF that's all wonky shaped and irregular, and then you're basically using the wavefront information. You get a nice circular wavefront, nice sharp PSF. This is what we're looking for. So all of this data will become public. The next upcoming data releases are the one to keep attention on is the release of all of the on-SkAI commissioning data from LSSTCam. That's coming in July through September this year. We've already released the data from the commissioning camera on SkAI campaign. That was data preview 1. We've now started the public alert stream. So if you're interested in actually, figuring out, what data products are going to be available, when they will become available, there's a document that describes how to access all of this data, what to expect, and the timelines for the data delivery. These are those timelines we were just discussing. And then the core question that we're dealing with right now is the considerations for the start of the LSST. So, within the Rubin team, we're constantly evaluating the performance. We're thinking about the effective survey speed. We're thinking about the distribution of the delivered image quality. We're thinking about how much expected improvements we can get from more dedicated on-SkAI engineering. We're thinking really critically about the team dynamics. We've been at this for many years now, and when you think about the system, you really have to think about it in terms of the hardware, the software, and the humans that animate the facility. Basically, none of this is possible without the team that's doing the work. There's the template generation for difference imaging, the survey strategy for the first year, the data management and the annual data releases, and the science community. Basically, there's thousands of scientists who are waiting to write grant proposals, early career scientists that are looking to write papers to help them get the next position. And scientific discoveries that strengthen the case to really go forward with this 10-year survey. So we're taking all this into account, but there hasn't yet been a decision on the start date of LSST. I was really hoping that when I came here today in April that I'd be able to tell you, but it's still a work in progress. So I want to make sure that we leave time. So let me just go to the summary and say that the past year of on-SkAI commissioning and early operations have effectively demonstrated all the operational aspects of Rubin Observatory. We've been able to survey the sky continuously for many nights. We've shown all of the different engineering modes. We've shown all of the generation of science-ready data products and have started distributing those to the community. The as-built observatory is capable of delivering data products that meet the science performance goals of LSST. We know that it has that capability. And what we're working on now is that sustained, reliable, and repeatable performance so that we're confident that it's a good investment for the broad science community to begin the 10-year survey. And we're looking into exploring all the different options that we can continue to improve the performance while starting the survey as soon as possible. I'll stop there. Thanks.
Excellent. Thanks, Keith. I want to say a couple of things. First, I forgot to say that in addition to all of this, Keith also does near-field cosmology and is really interested in dark matter. So if you're interested in that, you should talk to him. And the other thing was I was happy to see that this is the 1-year anniversary of, I guess, LSST Cam, in addition to tax day. So yes, many things are coinciding. All right. Any questions?
Yeah.
Hi, Keith. This is Adam Miller from Northwestern. Can you talk a little bit? I know that there's a few different places where AI systems are being integrated in terms of helping the telescope believe there's one module for the AOS, but I think there's some others as well. And can you describe those briefly? We have a number of computer scientists in the audience that might be interested to hear about that.
Yeah, for sure. So I would say that using machine learning models, basically training them on the donut images. So if we go back and look at some of these donut images, right? In some sense, this is almost an ideal problem for machine learning, right? Because you have this very large, high-dimensional space that you're trying to explore. You can generate lots of simulations. You can generate lots of on-SkAI data that you can use for training, right? So we can generate huge amounts of data, and you can basically there's a well-defined success criteria, right? Which is how well you can predict the PSF and how sharp you can make the PSF. So we actually have two different machine learning methods that we're approaching, right? That we're actively using and testing right now. Neither is the baseline for doing the AOS, but we have tested these methods on SkAI. So one of them is using our conventional forward modeling approach for the donut images, and it's basically using that forward model to create the training set to train the machine learning model. So the reason for doing that is that we believe that the machine learning model, it may have more rapid convergence, and it just runs faster. And the faster we can do the wavefront estimation, the sooner we can apply the corrections, and so it makes the closed loop task easier. We're also using an AI a machine learning method for donut fitting that's actually trained completely independently. So it's trained just on simulated images. And so that's really a completely different algorithm and different approach. And so one of the main goals of that is actually to compare the performance of that independent method with the conventional forward modeling approach. I would say just anecdotally, even within the past few months, there have been a lot of scientists in Rubin who have started using large language models for writing code. It has had a remarkable impact on more and more people getting involved in these analyses. Like we just generate this like huge amount of data and like huge amounts of telemetry, and like sifting through it and like figuring out what to do next. It's really challenging, but people have gotten to the point now where like people who is like an expert senior scientist, like our former director, Željko Avezic, right? He's been really busy with director stuff, and he's like extremely, respected, well-regarded scientist. But he hasn't had as much time to like directly write the code for getting into the science pipelines. But he has ideas for what to do, right? So he can basically tell one of these large language models, like, this is the analysis that I want to do. It has access to all of the open source code repositories and all the documentation for Rubin. And it basically is aware of all of our internal functions for accessing data. So you can write, natural language instructions, and it basically will generate entire analysis pipelines in a matter of minutes. And so just in terms of our ability to analyze and make sense of all this data, more and more people are using those techniques. And I'd say that's actually kind of a qualitative shift that's happened even on the timescale of the last 2 to 3 months. I don't know if that's helpful, but it's been eye-opening to me. Maybe it's old news here.
Any other questions for Keith? Okay, I have a very short one, so just so that people get to lunch. So what is the thinking now about this kind of AOS solution? Whether it is just like the space of degeneracy is way too large, or it's that you're not optimizing the right thing?
So our current hypothesis is that maybe it's easiest to explain actually looking at this. There's variations of the optical aberrations across the field of view. We have the 4 corner wavefront sensors, right?
It's not enough.
So basically, variations across the field of view that can be expressed in terms of like a piston and a tip and tilt, right? We can constrain well, but there's more and more evidence that we've been able to gather that there may be higher order spatial variations across the field of view. and that the information from the corner wavefront sensors alone is not enough to constrain these. And it's possible that the system is basically either getting into like a local minimum, or that it's like trying to force itself and like alternate like between states and creates this oscillatory pattern that's just not well constrained. So what we're doing to address that is that we're taking observations where we actually intentionally piston the entire focal plane slightly out of focus to basically so that we get these donut images across the full field of view. And so the idea is that we will be able to create like a model for how to correct those aberrations, and basically put that into our lookup tables or put it into our intrinsic aberrations model so that we can correct for those. And so like a lot of the testing that we're doing in recent weeks is basically establishing how consistent are those optical aberrations, like as we're moving across, different positions and like telescope pointing coordinates, how quickly do they vary with time? How reliably can we predict what those aberrations would be without needing to rely exclusively on the four corner wavefront sensors.
Excellent. I think we should go to lunch. I think students and postdocs, you're welcome to get lunch with Keith. Yeah. And I think we have a present from SkAI that Hinema is gonna present to you. As a souvenir. You drove all the way down. All right. So thanks everyone.
Yeah,
and see you around.
Thank you.